In this video, I will be solving a problem for Nyquist stability criteria. Okay, so we have a transfer function here k by s into s plus 2 into s plus 4. Sketch the Nyquist plot and hence calculate the range of values of k for stability. So how we will be doing this? We have already seen the theory for Nyquist stability criteria. Now we'll see how to apply that to solve a problem. So here in the given transfer function, first we have to check how many poles and zeros are lying on the right hand side of the S-plane, because we are bothered only about the right hand poles or zeros. Now we'll just see the first one, the number of poles on right hand side. So the poles here, it is, we can see it is 0, then -2 and -4. We can see that all the poles are lying on left hand side and one is at origin. So we just need to, so number of poles lying on right hand side for this particular transfer function p is equal to 0. So by Nyquist stability criteria, we know the number of encirclements about the critical point -1 j0 should not get encircled by the Nyquist plot, because n is equal to minus p. So here p is equal to 0, so that is equal to 0. This means that the number of encirclement of -1 j0 point by the Nyquist contour should be 0. Now we can just start doing how to do this. Now this is the stability criteria. The encirclement of origin should be -1 j0 point should be 0. We'll just see the we'll plot this one. Now we know that there is a pole present at origin, so we have a pole present here. Now as I already told you, what we are doing in Nyquist plot is like we will be mapping the entire right side of S-plane into a new plane, that is called as Nyquist plot. So we have the entire right hand side of the S-plane. So this one is our S-plane. This is S-plane, okay, and in the given transfer function we have a pole at origin, so we have marked that one. Now here we know that the contour or the plane which we are considering, it is starting from plus j omega and it is going up to minus j omega. So here we can see that there is a pole present at origin. So what we have to do is we have to bypass that pole, because this is the singularity of the transfer function. The pole is the singularity of the transfer function. So when you do that, we have this sessions, okay. So we are bypassing this pole, so we can divide this into various regions. Now 1, 2, 3, and I am just dividing it into 4 sections. Now what we have to do is we have to plot the polar plot separately for this sections 1, 2, 3 and 4. So for that, what I'll be doing is, first we need to, this one is plotting is done. Now fourth point is like, now here it is in S-plane, that is the transfer function given is in S domain. Now for plotting polar plot, we know that we have to we have to find the magnitude of the transfer function, and also we have to find the phase angle of the transfer function. So for finding that, we'll be substituting S is equal to j omega. So when you substitute S is equal to j omega, we'll be getting gj omega, hj omega is equal to, we have to substitute S is equal to j omega in the given transfer function. So we'll be getting it as k divided by, instead of S, we'll be having j omega. We have S into S plus 2, so we'll be having j omega plus 2, and we have j omega plus 10. Okay, so this is our transfer function. Now for finding the magnitude, what we'll be doing is magnitude. Okay, I can just write this as, I'll be rewriting, because we just need to have S plus jy form, let it be. So we can have j omega. So this is just rewriting those factor in this x plus jy form, 10 plus j omega. So we got the transfer function like this in j omega. Now for finding magnitude of this one is nothing but, because for polar plot we need to find the magnitude and phase angle. Because why we need polar plot? Because for plotting this Nyquist plot, we have to plot this polar plot for this various sections 1, 2, 3 and 4. That is the mapping. Mapping is nothing but it is a polar plot drawn for those sections marked. Okay, I didn't mark this one. Let let me mark this, this is the origin, so I can just mark this as minus j0, sorry, plus j0, and here it is minus j0. Okay, so 2 points we got there, plus j omega, plus j0, minus j0, and minus j omega. So now will be here magnitude, we'll be getting it as k divided by, for x plus jy we know magnitude is equal to square root of x square plus y square, and angle is nothing but tan inverse y by x. Okay, so this is what we are going to apply here. So we'll be getting k divided by omega into square root of 4 plus omega square to square root of 10 square plus omega square. This is the magnitude we are getting. And what about phase angle? Phase angle is this one, tan inverse 0 by k, because this is k plus j0, divided by tan inverse omega by 0 to tan inverse the second term, that is omega by 2, this one, then tan inverse omega by 10. So this is the phase angle we are getting. Okay, so here tan inverse 0, that is 0. Here in the denominator you have tan inverse infinity is coming. Tan inverse infinity is nothing but it is 90 degree. So when it comes to the numerator, you will be getting it as minus 90. So minus 90, tan 90 is infinity. So when you are taking that to numerator, it is becoming minus 90. And this one, tan inverse omega by 2, when you are taking to numerator, we will be getting a negative sign, tan inverse minus tan inverse omega by 2 minus tan inverse omega by 10. So this is the formula for finding the phase angle, and this is the formula for finding the magnitude for drawing the polar plot. So we will be considering the sections. So section 1. So what is that section here? Section 1, we know it is starting from s is equal to plus j omega, and it is going up to plus j0. Okay, so omega is from, sorry, this is instead of j omega, here actually it is where omega is infinity. So this one I should make it as plus j infinity, and it should go to minus j infinity, because it is, we are considering the entire right half of s plane. So it is omega is infinity. So j plus j infinity to minus j infinity. So section 1 will be having s is equal to plus j infinity, and it is going up to s is equal to plus j0, which means that omega is infinity and omega is 0. So for finding that one, for omega is equal to, so starting point is nothing but it is omega is equal to infinity. So when omega is tending to infinity, we have to find the magnitude. So what is our magnitude when omega is equal to infinity? Here, when you substitute omega is equal to infinity in the magnitude equation, you will be getting infinity in the denominator. So the value becomes 0. So magnitude is equal to 0. And what about angle? Angle is minus 90 degree minus tan inverse omega is infinity. We are substituting infinity first. Tan inverse infinity minus tan inverse infinity. So minus 90. So angle is nothing but minus 90 minus 90 minus 90. So it is minus 270 degree. Minus 270 degree you are getting. So we can write it as this 0 angle minus 270 degree. This is for plotting polar plot. And end point is, end point we know it is omega is equal to 0. So omega is equal to 0. So when you substitute omega is equal to 0 in the magnitude plot, you will be getting magnitude as infinity. That is something divided by 0, you will be getting infinite as the value. And in the phase angle equation, when you substitute omega is equal to 0, you'll be getting minus 90 degree minus tan inverse 0 minus tan inverse 0. So you'll be getting the angle as phi is equal to minus 90 degree. So here the value is infinity angle minus 90 degree. So this is our first section. Okay, now section 2. Section 2. Okay, section 1, if we want to draw the polar plot, we will be getting, okay, let me draw it here. So starting point is magnitude is 0 and angle is -2. Minus angle we are taking in the clockwise direction. So here it is minus 90 degree, here it is minus 180 degree, here it is minus 270 degree. So starting point, the magnitude is 0 and it is going in the angle 270, and end point is infinite and angle in minus 90. So it will be going in, end point is here. It will be starting from here and it will be going like this. We can see that it will be something like this. You will be getting the polar plot. Now section 2, we know which is the section 2. Section 2 here you can see it is from J0 plus J0, it is going to minus J0. So omega is from 0 to 0. So it is like, just draw here. Section 2 we have S is equal to plus J0 and it is going to J0. S is equal to minus J0. Okay, so it is omega is from plus 0 to omega is going to minus 0. Okay, so now starting point you have omega is equal to plus 0. So when you substitute it here, when omega is equal to 0, you will be getting magnitude as infinite, and when you substitute omega is equal to 0 in this angle equation, you will be getting the angle as minus 90 degrees. So you will be getting the angle as magnitude as infinite and angle as minus 90 degrees. So this is a starting point, and end point we have omega is equal to minus 0. So I'll be getting here minus 0. So this one is tan inverse minus. So he will be getting it as, when here for terminating point, when you consider it as a negative, then the magnitude will be same but the angle is in the opposite direction. So we can consider plus 90 there. So how it will be coming is like from plus 90. So the starting point is minus 90 and the end point is plus 90. So where is our positive angle? So here plus 90 comes here, plus 90 degree. So it will be starting somewhere here and it is going to plus 90. Okay, so this plot is not proper. I'll redraw it downwards. Okay, so here it is plus 90 because it is. So this is our section 1. This is the plot for section 2. And when we consider section 3, just see what is our section 3 here. Section 3, it is starting from minus J0 and it is going to minus J infinity. You can just see that section 1 and section 3. So if section 3 is just the mirror image of section 1, so you need not find the values, you just draw the mirror image of that one. Okay, so you can just draw the mirror image of section. So section 4 is, section 3 is mirror image of section 1. So what I'll be getting here, I'll be redrawing it again. Okay, you can just draw. I'll just draw it here. Proper plot. This is section 1. It is going in this direction. Okay, section 1 we have already drawn. This is section, sorry, this is section 2. This is section 2. Then we have section 3, that is nothing but it is a mirror image of this one. So mirror image means it is just be drawing like this. It is just the mirror image. Okay, so section 2, this is here. This is section 3. We got section 3 also. I have just drawn the mirror image of that one. Actually, this plot is not looking properly. I'll just redraw it. Wait. I'll just draw it again. It is not, you can't clearly understand from that diagram. Okay, I'll just draw it here. Then this is our second plot, second one, then this one. Okay. This is better now. Okay. This one is first section. This is second section, and this is our third section. Okay. Now, section 4. Section 4, if you see, what is there in section 4? Okay, section 4, it is starting from minus j infinity to plus j infinity. It is going like this in section 4. So when you substitute omega is equal to infinity here in the magnitude, the value becomes, the denominator is infinity, so the value becomes 0 there. And here when in the phase angle, it is showing when you are putting minus 90, minus 90, minus 90, so it is minus 270. So you know it is like for section 4, anyway the magnitude is infinity, so we'll be getting it at the origin only. Okay, the value will be getting at origin because the magnitude is 0. So both the values, so it is at section 4 is at origin. Now the next step is like, now what is the Nyquist stability criteria? Now we have drawn the Nyquist plot. Here you can see that now we need to find it out. This one, just let me put the here. Okay, the number of encirclement of this point minus 1 j0. So here in this particular problem, there are no right hand side poles. That means np is equal to 0. So n is equal to minus p, which gives the condition n is equal to 0. That means there shouldn't be any encirclement of this minus 1 j0 point by this contour. So now that means that for the system to be stable, let me mark this points as, let me mark this one as O. This point, let it be Q. So this Q point, if it is this minus 1 j0 shouldn't come inside this one, because according for the stability condition, the number of encirclement should be 0. So how will you find that? So for finding this, you know, this one OQ, this point, we need to find the magnitude at the point Q. So we need to prove that the magnitude is less than minus 1. So then only we can say that it is coming within minus 1. Then only we can say that the system is stable, otherwise the system is unstable. So we need to find this magnitude of this the value of at this point Q. So for finding that, we can find the magnitude of OQ. Will you find the magnitude of OQ? We have the transfer function here. Okay, so transfer function magnitude value we know here, and at this particular point we know at this point Q the imaginary value is 0 because it is lying on the real axis and the angle is 180 degrees. So here in this particular case, we can find OQ by equating the imaginary part to 0. Equating the imaginary part to 0 because Q point doesn't have imaginary part because it is lying on real axis. So what we do is, for equating the imaginary part to 0, we need to rationalize the equation. So we already have Gj omega, Hj omega. So that transfer function we can rationalize so that we can separate the real and imaginary part. So it is k by j omega into, this already is given the question, 10 j omega into 2 plus j omega. This is our transfer function which is given. So we are going to rationalize this transfer function so as to separate the real and imaginary part. Why we are rationalizing? Because we want to equate the imaginary part to 0 so that we can find the point Q. So rationalizing, how will you rationalize? So for rationalizing, what we do is we'll be multiplying and dividing by the complement of that factor. Okay, so when you rationalize it, the G, you will be getting Gj omega, Hj omega as is equal to k into, we are multiplying and dividing by the complement, so it is j omega complement is minus j omega. 10 plus j omega complement is 10 minus j omega. That is a complex conjugate. Can say the complex conjugate. So 2 minus j omega. We are multiplying and dividing by the complex conjugate of that particular factor. So when we divide minus j omega, we have to multiply it. Then 10 plus j omega into 10 minus j omega. So 2 plus j omega into 2 minus j omega. So those are the factors we are getting. Now we just simplifying this equation. I will be getting it as, just simplify it by multiplying it. So I'll be getting, I'm just skipping the step. It is just when you simplify it, you will be getting like this: 20 minus 12 j omega minus omega square in the numerator, and in the denominator you will be getting it as omega square into 4 plus omega square into 100 plus omega square. We are just multiplying the factors. That is 10 plus j omega into 10 minus j omega. You can take it as a plus b into a minus b form. That is a square minus b square. Everything we are doing like that. Okay, so here again we are multiplying. We are taking the real part and imaginary part separately. So multiply it and find the real and imaginary part. So 12k omega square divided by d minus, I'm just writing it as d, denominator I don't want to repeat it, that's why, and for simplification purpose I'm writing like this, into 20 minus omega square divided by d. What is this d? D is nothing but it is our denominator, where d is omega square into 4 plus omega square into 100 plus omega square. D is our denominator, the same thing. Okay. So, okay. Now what we have to do? We have to equate the imaginary part to 0. Here what is our imaginary part? Imaginary part is this k omega into 20 minus omega square. So we are equating imaginary part to 0. Imaginary part to 0 will be getting it as omega into 20 minus omega square, that is k omega into 20 minus omega square by d is equal to 0. So with this we'll be getting 20 minus omega square, because remaining all will be cancelling. This is equal to 0. From this we'll be getting it as omega is equal to square root of 20. So we know this is the value of frequency when the magnitude is becoming that one. You can just see it is the plot is cutting the S-plane at 180 degrees. So that is the phase crossover frequency. So this is nothing but nothing but it is our phase crossover frequency. So if we substitute this omega, this one, in the real part of this one, the equation, okay, real part is 12k omega square by d. So substituting this value in, substitute in real part, we'll be getting the point q as, point q is equal to, that real part is what? Minus 12k omega square by d. So minus 12k omega square, omega is square root of 20, omega square is 20. So 12k omega square divided by d. D is omega square, that is 20, into 4 plus omega square. D is 4 plus 20 into 100 plus 20. So this is the value we are getting. Now when you evaluate this one, we'll be getting it as minus k by 240. Okay, so this is the value we are getting here. Now how will you find the value? What is asked in the question here? You just see this one question: sketch the Nyquist plot and hence calculate the range of values of k for stability. So we know that for here n is equal to n. For the system to be stable, we need to have n is equal to 0. Since why it is n is equal to 0? Because there are no right hand side poles lying on right hand side of S plane. So n should be equal to 0. So what we do is, now we know this, we need to find the value of OQ here. So for system to be stable, we obviously know that this OQ value should be less than 1. The magnitude should be less than 1 because a -1 should lie outside that region. So we'll be applying that condition for absolute stability. For absolute stability, we need to have n is equal to 0, that the encirclement should be equal to 0. So it should be located on left side of the point Q. That is, -1 should be on the left side of Q. So OQ, the magnitude of OQ should be obviously less than 1. So what is the magnitude? Here we got the point Q as minus K by 240. So magnitude is K by 240. So in that case, K by 240 should be less than 1 for stability. So this means, which gives us K should be less than 240. So the range of value of K for stability is nothing but K should be greater than, K is obviously greater than 0, and it should be less than 240. So this is the range of value of K for 240. How did you get that? It is why we got this value like this, because we know that for stability, this -1 should lie outside. -1 should be somewhere here, because if it lies inside, then this contour, this Nyquist plot will be encircling that -1. So according to the Nyquist stability criteria, we need to have n is equal to 0. That is, there shouldn't be any encirclement of -1 or J0 point. So that is why OQ, for checking the value for the range of values for the K for the stability, what we have done is, we have found the magnitude of the distance OQ. So we need to have that value OQ should be less than 1, so that we can understand that the 1 will be lying outside the left -1 will be on the left hand side of point Q. So we substituted that condition here, and we found the value of K for stability, and we found that the value of K should lie between, K should be greater than 0 and less than 240 for the systems to be stable. So this is how you can solve a problem using Nyquist stability criteria. Okay, I hope you understood how to solve a problem using Nyquist stability criteria. Thank you.